Comets are supposed to fade as they leave the sun. That's the rule. Solar energy decreases, sublimation stops, the show ends. Except 3i Atlas didn't get the memo. Right now, as it coasts toward the outer solar system, it's getting brighter, more active, more structured, and scientists are running out of natural explanations. The Hubble Space Telescope captured something in December 2025 that shouldn't exist. Mirror-symmetric jets that realign after gravitational deflection, dust moving at impossible speeds, and an anti-tail that refuses to fade. Either we're missing something fundamental about cometary physics, or we're watching something that was never a comet at all. Stay until the end, because what Jupiter reveals in March might change everything we thought we knew about what visits our solar system. Hit subscribe and stay with us as we piece this together, data point by data point. 3i Atlas is still out there, still heading toward Jupiter, still breaking every rule we thought we understood about how these objects behave. Fresh observations arrive constantly, and when the full picture finally emerges, you won't want to miss it. March 2026 is approaching. Make sure you're here when the truth reveals itself. Something is moving through our solar system that refuses to follow the rules. 3i Atlas, an interstellar visitor from beyond our cosmic neighborhood, is currently coasting away from the sun, and it's getting brighter, more active, more structured, which would be perfectly fine if comets were supposed to do that, but they're not. Comets fade as they retreat. They dim. They quiet down. They don't organize themselves into complex geometric patterns, while the energy that drives them disappears behind them. So either our understanding of cometary physics has a fundamental gap, or something else is going on. Perihelion already happened. That's the moment when a comet swings closest to the sun and soaks up maximum solar radiation. It's the grand finale of cometary activity, the moment when all that frozen material starts sublimating into space, producing those iconic tails and glowing envelopes. After perihelion, the comet retreats. The sun gets smaller in its sky. The energy input drops. And so does the show. That's how it works. That's how it's always worked, except 3i Atlas didn't get the memo. In December of 2025, the Hubble Space Telescope turned its Wide Field Camera 3 toward this object and captured something that made astronomers lean closer to their monitors. The team used rotation gradient filtering and stacked exposures to pull out fine details. And what they saw was an object that wasn't winding down. It was ramping up. The anti-tail, that sunward pointing column of dust that usually appears as a brief optical illusion caused by our viewing angle, was not only real, but enormous, larger and brighter than both the dust tail and the ion tail. And it wasn't fading. It was dominating the entire structure. Then there were the jets. 2 of them, sharp and defined, carving through space with geometric precision. But here's the thing about jets. They're supposed to diffuse. As comets spin and tumble through space, their jets spread out, blur, lose definition. These jets were doing the opposite. They were sharpening, evolving, changing configuration in under 15 days. That's not how passive outgassing behaves. That's not how thermal processes respond to decreasing solar input. The language in the observation notes started to shift. Early reports talked about dust distribution and sublimation patterns. By December, the terminology had changed. Now they were describing directed outflow and persistent structures. That might not sound like much, but in the careful world of scientific reporting, word choice matters. When astronomers stop using neutral descriptors and start using words that imply agency or direction, it means something in the data is making them uncomfortable. The energy problem is straightforward. Solar heating is decreasing. The object is moving away from the primary energy source, and yet activity is increasing. This isn't a subtle effect. This isn't noise in the data or a calibration error. This is a clear, measurable inversion of expected behavior. And before anyone suggests it, no, this isn't fragmentation. There's no debris field, no breakup signature, no evidence of structural collapse. It's also not observational error. Hubble doesn't make mistakes like this. And it's not background contamination. The structures are moving with the object, evolving in real time, responding to something. Here's where the interstellar origin becomes crucial. Long-period comets from our own Oort cloud have a thermal history. They've been orbiting the sun for billions of years, even if those orbits take millennia to complete. They've been baked and frozen in predictable cycles. But interstellar objects, they have no relationship with our sun. They're visitors from another stellar system, carrying ice chemistries and thermal properties that might be completely alien to what we've observed before. That opens the door to exotic volatiles, unusual compositions, maybe even structural configurations we've never encountered. But even accounting for that, the inversion remains. Even if 3I Atlas is made of some unknown ice that sublimates at lower temperatures, you still need energy. You still need a driver, and the driver is moving away. If this were a normal comet behaving this way, scientists would question the data. They'd check the instruments, review the analysis, look for errors. But because this is an interstellar object, they're questioning physics instead, which is either a sign of appropriate scientific caution or a subtle admission that something genuinely strange is happening. Activity is increasing. That's the baseline fact. But if the activity is increasing, then the geometry matters. The direction of the jets matters. The orientation of the anti-tail matters. And when you start looking at the geometry, that's when things stop making sense entirely. Because what Hubble saw in December should not be possible unless this object is either spinning in a way that defies rotational dynamics, or the jets aren't being controlled by rotation at all. Let's reconstruct what happened. Back in July of 2025, when 3I Atlas was approaching perihelion, astronomers observed a prominent sunward jet. This is normal. Comets develop jets on the side facing the sun because that's where the heating occurs. The jet was measured, tracked, and analyzed. Scientists noted the wobble in its orientation, the way it shifted slightly as the object rotated. Everything behaved as expected. Then 3I Atlas swung around the sun. During that close approach, the sun's gravity bent the object's trajectory by approximately 16 degrees. That's a significant deflection. And when you deflect an object's path by 16 degrees, you also change its orientation relative to the sun. Imagine holding a spinning top and suddenly shifting the direction it's moving. The top doesn't realign itself instantly. Its spin axis stays roughly where it was, even as its trajectory changes. For 3I Atlas, that means the original sunward jet, the one that was facing the sun in July, should now be pointing at least partially away from it. Hubble's December observations should have shown a weakened or absent sunward jet, possibly some residual activity from the now misaligned heating pattern. Instead, they found a new, stronger sunward jet on the opposite hemisphere, pointing directly at the sun despite the changed trajectory. It's as if the object looked at where the sun was after the deflection and said, "Okay, let me reconfigure." This is mirror image symmetry. Same behavior, opposite orientation. The jets aren't just persisting. They're recreating themselves in response to the object's new geometry relative to the sun. And that shouldn't happen. Rotational wobble doesn't work this way. If the object is tumbling, jets would smear across the surface, creating broad, diffuse patterns. They wouldn't sharpen. They wouldn't reappear symmetrically. The timescale is wrong too. The deflection happened over days. Rotational wobble takes weeks or months to produce observable changes in jet orientation. Then there's the anti-tail. That massive, sunward-pointing column of dust that's dominating the whole structure. It's still pointing directly at the sun. Despite the orientation change, despite the trajectory adjustment, Anti-tails are supposed to be perspective effects, the result of dust particles reflecting sunlight in a specific geometry. But this one has remained locked onto the sun through a 16-degree course change. Either it's realigning faster than rotation allows, or it's not controlled by rotation at all. No known comet has shown this behavior. Scientists have studied hundreds of comets, tracked them through perihelion, watched them respond to solar deflection. None of them have produced mirror-symmetric jets after a gravitational bend. None of them have maintained anti-tail alignment through significant trajectory changes. This is new. This is anomalous, and it presents a very uncomfortable choice. Either our understanding of how thermal activity drives cometary jets is fundamentally incomplete, or the orientation of 3I Atlas relative to the Sun is somehow irrelevant to where its jets appear. That second option should sound wrong, because it is wrong. In conventional comet physics, orientation is everything. You heat one side, you get activity on that side. The object rotates, the heated region moves, the activity shifts. It's direct cause and effect. But if 3I Atlas is producing jets that don't care about which side is facing the sun, then the jets aren't being driven by surface heating alone. Something else is involved, some other mechanism that can respond to the sun's direction, regardless of how the object is spinning. Scientists are being very careful with their language here. They're not claiming anything extraordinary. They're simply noting that the observed jet behavior does not match rotational models. They're pointing out that the symmetry is unexpected. They're admitting that the timescale of jet evolution is faster than thermal conduction can explain. These are factual statements, but they're factual statements that point toward a gap in our understanding. And when that gap involves an object that's already defying expectations in multiple ways, people start to wonder. The geometry is wrong. The timing is wrong. The persistence is wrong. But to understand just how wrong things are, you need to look at the dust itself. Because the dust particles being ejected from 3I Atlas are doing something that should be physically impossible, unless they're being launched at speeds that no natural sublimation process can produce. Dust grain size is one of those details that sounds boring until you realize it's the key to everything. The dominant particle population in 3I Atlas's coma is approximately 10 microns in diameter. For context, that's about 1/10 the width of a human hair. Typical comet dust? Submicron to 1 micron grains. Tiny particles that scatter light efficiently and get pushed around easily by solar radiation pressure. 10 micron grains are different. They're big, heavy, and that changes everything. Radiation pressure works like this. Photons from the sun carry momentum. When they hit a dust grain, they transfer that momentum, pushing the grain away from the sun. For small particles, this is a powerful force. They get accelerated to high speeds, pushed outward in beautiful, sweeping dust tails. But radiation pressure scales with surface area and mass scales with volume. As grains get bigger, the ratio shifts. Larger grains have more mass per unit of surface area, which means they experience less acceleration from the same photon flux. 10 micron grains should stall quickly. Even if they're launched with decent initial velocities, radiation pressure alone can't sustain their outward motion for long. You'd expect them to decelerate, slow down, maybe persist for a few thousand kilometers before falling behind the object's motion. But the sunward column of dust, extending from 3I Atlas, reaches approximately 1 million kilometers. That's not a few thousand, that's a million. And for those grains to maintain structural coherence over that distance, they need to be moving fast. Really fast. Estimates suggest launch speeds approaching or exceeding 1 kilometer per second. That's the kind of velocity you'd need to keep 10 micron grains suspended against both radiation pressure and the object's own gravity long enough to form a 1 million kilometer structure. But here's the problem. Natural sublimation doesn't produce those speeds. When ice turns to gas on a comet's surface, the expanding gas drags dust particles along with it. Water ice sublimation? You get gas velocities around 300 to 400 meters per second. Carbon dioxide can push that to maybe 500. Carbon monoxide, in the most optimistic scenarios, might reach 600. 1 kilometer per second is double that. It's not just higher than expected. It's higher than the known limits of sublimation-driven outflows. You can't explain it by invoking exotic ices, because even the most volatile materials have thermodynamic limits. You can't explain it with perfect geometry, because even a perfectly aimed jet is still constrained by the energy available from phase transitions. The math doesn't close. The energy isn't there, unless something else is accelerating the dust after it leaves the surface. Some secondary process that adds velocity beyond what sublimation provides. And before anyone suggests it, yes, there are natural mechanisms that might contribute. Gas drag in the inner coma could provide additional acceleration. Electrostatic forces between charged particles might play a role, but these are incremental effects. They don't double the velocity. They don't bridge the gap between 500 meters per second and 1 kilometer per second. Large dust grains have another interesting property. They're very good at reflecting light. That makes them efficient shields. If you wanted to obscure something, surrounding it with 10-micron particles would do the job nicely. Not opaque enough to completely block light, but opaque enough to blur details, scatter photons, create a marginally opaque envelope that prevents clear observation of whatever's underneath. Which brings us to an uncomfortable question. What if we're not seeing the nucleus at all? Every estimate of 3I Atlas's nucleus size is based on brightness measurements. Astronomers look at how much light the object reflects, compare it to typical cometary albedo values, and back-calculate the size. The current estimate is about 2 kilometers in diameter, but that assumes ordinary reflectivity and a transparent coma. If the coma is marginally opaque, if there's a maintained dust layer between us and the central body, then those estimates are minimums. The actual nucleus could be larger, or smaller, or not a nucleus in the conventional sense at all. This is where speculation starts to creep in, and scientists are being very careful to label it as such. They're not claiming anything definitive. They're simply noting that the dust distribution around 3I Atlas doesn't behave like a passive debris cloud. It's organized, persistent, and conveniently positioned to obscure the central object. That could be coincidence. Natural processes can produce organized structures, but when you combine it with the jet symmetry, the energy inversion, the impossible velocities, the pattern starts to look less random and more functional. We may not be observing a comet at all. We may be observing an interface, a boundary layer between something hidden and the space around it. And if that's true, then every model we're using to explain this object's behavior is based on a false assumption. Brightness-based size estimates are how we measure most distant objects in space. You can't send a ruler to a comet, so you do the next best thing. You measure how much light it reflects. Brighter objects are either larger or more reflective, and since you can make reasonable assumptions about cometary reflectivity based on hundreds of previous observations, you can work backward to estimate size. For 3I Atlas, that calculation gives you about 2 kilometers. But there's a critical assumption embedded in that number. It assumes you're seeing the nucleus. Marginal opacity changes everything. The coma around 3I Atlas isn't opaque enough to completely block light from reaching us. If it were, the object would appear as a dark void against the background stars. But it is opaque enough to scatter, diffuse, and blur the light that passes through it. Imagine trying to see a light bulb through frosted glass. You can see that something is glowing, but you can't make out the shape of the bulb itself. The brightness you observe is a combination of the bulb and the scattering effects of the glass. This is the false fuzzball effect. The object appears comet-like. It has a coma, it has tails, it glows in exactly the way comets glow. But the central brightness, the core that we're using to estimate size, might not be the nucleus at all. It might be an artifact of the dust envelope, a scattering signature that looks like a solid body, but is actually a maintained boundary layer. And if that's the case, we have no idea what's underneath. Historical parallels exist. There have been comets whose comae concealed unexpected interiors. Comet Schwarzmann-Wachmann 1, for example, maintains a permanent coma that makes it nearly impossible to observe the nucleus directly. Comet 17P/Holmes underwent an outburst that increased its brightness by a factor of 500,000, temporarily obscuring its nucleus behind a massive dust cloud. But those were exceptional events. Outbursts. Temporary states. 3I Atlas isn't having an outburst. This is its baseline behavior. What's more troubling is the absence of fragmentation. High cometary activity usually produces structural stress. As volatiles sublimate and jets fire, they exert torque on the nucleus. Small comets, or loosely bound objects, often break apart under this stress. We've seen it happen dozens of times, but 3I Atlas shows no signs of fragmentation. No debris field. No secondary objects. Despite activity levels that should be tearing it apart, it remains coherent, intact. The jets persist without causing collapse. That suggests structural integrity beyond what you'd expect from a loose rubble pile. Either the nucleus is unusually dense and well-bound, or it's being held together by something other than gravity and tensile strength. Again, there are natural explanations. Maybe it's a solid chunk of ice rather than a rubble pile. Maybe the composition is unusually cohesive. But combined with everything else, the structural coherence adds another item to the list of things that don't quite fit. The controversial idea that keeps surfacing, the one scientists discuss in private, but rarely put in papers, is that the dust envelope might be maintained. Not a passive cloud that happens to obscure the nucleus, but an actively managed interface designed to prevent observation. And yes, designed is a loaded word. It implies intention. Technology. Intelligence, which is why scientists are so hesitant to use it. But the alternative is to assume that all of these anomalies, the jet symmetry, the energy inversion, the impossible dust velocities, the structural coherence, are coincidences, natural quirks that happen to combine in ways that mimic purposeful behavior. We may not be observing a nucleus. We may be observing a controlled boundary between whatever 3I Atlas actually is and the outside universe. That's not evidence of technology. It's evidence that our models are incomplete. But incomplete in a very specific way. Incomplete in a way that makes the data look functional, purposeful, directed. At this point, scientists start lining up natural explanations, and every single one of them leaves something unresolved. Let's be clear about the rules. No straw men. No invoking aliens whenever something seems weird. Science works by proposing models, testing them against data, and seeing what holds up. For 3I Atlas, astronomers have proposed several natural explanations for its anomalous behavior. Each one solves part of the puzzle. None of them solve all of it. And that's the problem. When you're dealing with an object that defies expectations on multiple independent axes, you start running out of coincidences to invoke. Model 1. Deep thermal conduction. Maybe the object isn't responding to surface heating at all. Maybe heat is being conducted deep into the interior during perihelion, and now that stored energy is slowly working its way back out, driving activity long after the object has retreated from the sun. This would explain the post-perihelion brightness increase. Thermal lag is a known phenomenon. Some comets continue active weeks after perihelion because of stored heat. Comet Hale-Bopp, for instance, remained bright for months after its closest approach to the sun in 1997, powered by heat slowly diffusing outward from its interior. The problem is geometry. Thermal conduction doesn't explain mirror-symmetric jets. It doesn't explain why jets realign after gravitational deflection. Heat diffuses. It spreads outward in all directions from the warm interior, following temperature gradients. It doesn't create sharp, directed structures that respond to orientation changes. If deep thermal conduction were the driver, you'd expect broad, diffuse activity patterns that gradually fade as the stored heat dissipates. You wouldn't expect geometrically precise jets that sharpen over time and recreate themselves symmetrically after the object's trajectory changes. The timescale is wrong too. Thermal diffusion through kilometers of ice happens slowly, over weeks or months, not days. The jet evolution we're seeing in 3I Atlas happens too quickly for pure thermal conduction to be the answer. Model 2. Particle size filtering. Maybe the coma acts as a natural filter, allowing only certain sizes of dust grains to escape while trapping others. As the object moves away from the sun, the filtering process changes, perhaps due to evolving gas pressures or shifting coma densities, producing the appearance of increasing activity. This explains the persistence of large grains. It explains why the dust distribution looks organized rather than random. Gas flow patterns could theoretically sort particles by size, allowing 10-micron grains to dominate the outflow while smaller particles get trapped in the inner coma. But it doesn't explain the velocities. Filtering can't add energy. Even if you perfectly sort particles by size, creating a beautiful, organized distribution of 10-micron grains, they're still moving at whatever speed sublimation provides. And that speed isn't high enough. You can rearrange particles, you can select which ones escape and which ones stay behind, but you can't accelerate them beyond the limits of the gas that's carrying them. The 1 kilometer per second velocities needed to maintain that million-kilometer sunward column simply aren't achievable through passive filtering of sublimation-driven outflows. You'd need an additional acceleration mechanism, and particle size filtering doesn't provide one. Model 3. Rotational torque. Maybe the jets are producing asymmetric thrust, like tiny rocket engines firing from the surface. As gas and dust shoot out in specific directions, they exert reactive forces on the nucleus, changing the object's spin state. As the rotation evolves, different regions of the surface become exposed to sunlight, creating the appearance of new jets while old ones fade. This is absolutely a real phenomenon. Comet 67, P/Churyumov. Gerasimenko, studied up close by the Rosetta spacecraft, showed clear evidence of rotation changes driven by jet activity. This explains the brightness modulation. It explains why activity patterns might shift over time as the object tumbles through space, but it doesn't explain the mirror symmetry. Torque-induced rotation changes are gradual, not sudden. You need sustained thrust over extended periods to measurably alter a kilometer-scale object's spin axis. They don't produce instantaneous realignment after a 16-degree deflection. The jets we're seeing in December aren't the result of slow rotational evolution. They appeared quickly, in the right configuration, pointing at the sun despite the changed trajectory. That's not how torque works. That's not how rotation responds to jet forces. Model 4. Exotic ices. Maybe 3I Atlas contains volatiles we've never observed before. Ices that sublimate at very low temperatures, remaining active even in the outer solar system, where water ice would be frozen solid, nitrogen ice, carbon monoxide ice, methane ice, maybe even molecular hydrogen ice if temperatures during its formation were low enough. This is plausible for an interstellar object. It comes from a different stellar system with a different chemistry, possibly formed in conditions we've never replicated in our own solar neighborhood. The compositions could be completely alien to what we're used to seeing. But exotic ices still obey thermodynamics. They still have finite sublimation energies. They still can't produce velocities that exceed their molecular limits. You can shift the temperature range, allowing activity to persist farther from the sun than water ice would permit. You can change the composition of the gas, and therefore the dust-to-gas ratio. But you can't bypass the fundamental energy constraints. Sublimation is a phase transition. The energy released when molecules break free from the ice, lattice translates directly into gas velocity through thermodynamic principles that don't change regardless of what molecule you're sublimating. Exotic ices give you different temperature profiles, not impossible velocities. Each model fails on at least one axis. Geometry, energy, timescale. You can mix and match, combine models, propose hybrid scenarios where multiple processes work together. Deep thermal conduction providing sustained heat, exotic ices sublimating at low temperatures, rotational torque shifting the orientation, particle filtering organizing the outflow. And scientists are doing exactly that. They're building increasingly complex frameworks to accommodate the data, stacking mechanisms on top of each other, tuning parameters to make everything fit. But there's a point where complexity becomes a red flag. When you need 4 or 5 interacting processes, each tuned to very specific parameters, all happening simultaneously on a single object, you start to wonder if you're explaining the data or explaining it away. There's a principle in science called Occam's razor. The simplest explanation that accounts for the observations is usually correct, but simplicity has to be balanced against completeness. A simple explanation that only accounts for half the data isn't better than a complex explanation that accounts for everything. The problem with 3i Atlas is that the simple explanations don't work, and the complex ones require so many moving parts that they start to feel contrived. You end up with frameworks that are technically possible, but statistically improbable. The phrase that keeps appearing in private discussions is missing physics. Not unknown forces, not new fundamental laws, just configurations we haven't encountered before. Structures or processes that fall within known physics, but combine in ways we haven't observed. Maybe there's a natural mechanism that produces mirror-symmetric jets through some combination of internal structure and external forces. Maybe there's a way to accelerate dust particles beyond sublimation limits, using electrostatic forces we haven't properly modeled. Maybe the whole thing is an elaborate natural phenomenon that just happens to look weird, because we've never seen this particular combination of conditions before. That's a reasonable position. Science has been surprised before. Pulsars seemed impossible until we understood neutron stars. Fast radio bursts were inexplicable until we developed better models of magnetar behavior. Nature is creative. The universe has more tricks than we've cataloged. But it's also the kind of phrasing you use when you want to keep the door open without committing to anything controversial. Missing physics sounds better than we don't know what's going on. It implies that the answer exists within established science. We just haven't found it yet. Which might be true. But it might also be a way to avoid uncomfortable alternatives. When all natural models strain under the weight of the data, alternative ideas start to appear. And the most controversial alternative is the one nobody wants to say out loud. What if 3i Atlas isn't entirely natural? What if some or all of its behavior involves technology? What if we're not looking at a comet with weird chemistry, but it's something designed to look like a comet while doing something else entirely? That's a thought experiment, not a claim. A way of exploring what the data might look like if the conventional framework is wrong. But thought experiments have a way of becoming hypotheses when the conventional framework keeps failing. The technological hypothesis actually explains everything. Mirror-symmetric jets, thrusters adjusting to maintain solar orientation, impossible dust velocities, active particle acceleration, post-perihelion activity increase, power systems independent of solar heating, structural coherence, engineering rather than frozen volatiles. It's simple, it's complete, and it accounts for every anomaly without requiring exotic physics or improbable coincidences. The only problem is that it requires accepting that we're looking at something artificial in our solar system, which is a conclusion most scientists would prefer to avoid. The uncertainty is real. There's no proof, no smoking gun, no observation that definitively rules out natural explanations or confirms technological ones. But the data also doesn't forbid the possibility. And in the absence of a natural model that accounts for everything without invoking multiple strained mechanisms, The technological hypothesis sits there, waiting, not endorsed, but not dismissed, mentioned in footnotes, discussed in conference hallways, considered privately by researchers who won't put it in papers because the professional cost is too high. Science is supposed to follow the evidence wherever it leads, but science is also done by humans with reputations, careers, and institutional pressures. Suggesting that an astronomical object might be technological is career suicide unless you have overwhelming evidence. So, researchers propose natural models, no matter how complex. They invoke missing physics, exotic compositions, unprecedented configurations. They do everything possible to make the data fit within conventional frameworks. And maybe they're right. Maybe 3I Atlas is just a really weird comet that happens to exhibit behavior we've never seen before. But maybe we're avoiding the obvious because the obvious is too uncomfortable to seriously consider. Whether natural or not, one thing is certain. Jupiter will not be gentle with whatever 3I Atlas turns out to be. March 2026 is circled on every planetary scientist's calendar. That's when 3I Atlas reaches its closest approach to Jupiter. Not a collision, not even particularly close by astronomical standards, but close enough to matter. Close enough that Jupiter's gravity will subject this object to stresses it hasn't experienced anywhere else in its journey through our solar system. And how it responds will tell us what it's made of, or what it's hiding. This isn't speculation. This is orbital mechanics. When you pass a massive planet, physics happens. And physics doesn't care about your theories or your discomfort with certain possibilities. Jupiter's Hill sphere is the region where the planet's gravity dominates over the sun's. It extends roughly 53 million kilometers from the planet's center, a gravitational bubble where Jupiter's influence overwhelms everything else. 3I Atlas will pass through this region, and when it does, it will experience tidal forces. Not catastrophic, planet-ripping tides like those that tear apart moons or pulverize asteroids that venture too close, but measurable gravitational gradients that pull differently on different parts of the object. For a natural comet, this creates stress. The near side gets pulled slightly more than the far side. It's a gentle gradient, but gentle is relative when you're talking about forces acting across kilometers of material. Rotation becomes unstable. Imagine spinning a ball on your finger while someone gently pushes different sides of it at different rates. The spin wobbles. It shifts. For a comet, this means the orientation changes. The spin axis precesses, and any jets tied to specific surface features get redirected. Jets get disrupted because the forces that were maintaining them, the balance between solar heating and rotational stability, get perturbed. If the object is weakly bound, if it's a rubble pile held together by gravity, and maybe some weak ice, it might even fragment. Jupiter has torn apart plenty of comets. It's not malicious, it's just massive. What happens to natural comets near Jupiter is well documented. Comet Shoemaker-Levy 9 broke into more than 20 pieces during a close approach in 1992, then crashed into Jupiter's atmosphere 2 years later in one of the most spectacular astronomical events ever observed. The impacts created Earth-sized dark spots in Jupiter's clouds, visible through backyard telescopes. It was planetary violence on a scale that reminded everyone just how dangerous gravity can be. Comet Brooks 2 shed material during a Jupiter flyby, creating a debris trail that persisted for years. The nucleus survived, but it left pieces of itself scattered along its orbit like breadcrumbs. Dozens of other comets have shown altered rotation states, disrupted jets, or structural changes after encountering Jupiter's gravity. Some emerged spinning faster, angular momentum redistributed by the tidal interaction. Others came out tumbling chaotically, their previously stable rotation replaced by complex wobbles. Jets that were strong and persistent before the encounter became weak and sporadic afterward. Surface features changed position relative to the spin axis. The planet is a stress test. It reveals weaknesses. It separates solid objects from rubble piles. It doesn't ask permission, and it doesn't make exceptions. For 3I Atlas, the March encounter will answer questions that spectroscopy and imaging can't. You can point every telescope on Earth at this object, measure its composition, track its jets, analyze its light curve, and you'll still be left with models and interpretations. But when it passes Jupiter, the models get tested against reality. If the jets are driven by passive thermal processes, if they're just sublimation responding to whatever residual heat remains in the nucleus, Jupiter's tidal forces should disrupt them. Rotation states will change, surface regions will shift, and the geometric precision we've been observing should degrade into chaos. The mirror symmetry should break. The anti-tail should wobble or disperse. The sharp directed jets should smear into diffuse outflows as the spin axis tumbles. If the structural integrity is due to natural cohesion, if this is just a particularly solid chunk of ice and rock held together by intermolecular forces, we should see stress fractures. Possibly fragmentation. Definitely some sign that the object is being pulled in different directions. Cracks might appear. Material might shed. The nucleus might elongate slightly as tidal forces stretch it. These are predictable, measurable outcomes. Natural comets respond to gravitational stress in specific ways, and we know what those ways look like because we've watched it happen before. But if the jets realign, if 3I Atlas adjusts its trajectory, maintains structural coherence, continues producing mirror-symmetric jets despite the gravitational chaos, that would be unexpected. That would suggest either a level of structural sophistication beyond normal cometary bodies, internal reinforcement that prevents tidal disruption, or active compensation. Thrusters, course correction, systems responding to external forces in real time, measuring the gravitational gradient, and adjusting behavior to maintain stability. Which is a very uncomfortable thing to say about an object we've been calling a comet. But discomfort doesn't change what the data might show. The magnetic environment matters too. Jupiter has the most powerful magnetic field in the solar system, extending millions of kilometers into space. It's not just gravity you have to worry about when you pass Jupiter. The magnetosphere is a roiling ocean of charged particles, electromagnetic fields, and radiation. Electrons get accelerated to near light speeds. Protons spiral along magnetic field lines. The radiation belts around Jupiter make Earth's Van Allen belts look gentle by comparison. Charged particles get trapped, accelerated, and funneled into radiation belts that would fry any unshielded electronics in minutes. This isn't theoretical. We know this because we've sent spacecraft there, and keeping them alive required careful shielding and trajectory planning. Natural comets are affected by this environment. Their ion tails, those straight blue streamers made of ionized gas, distort when they interact with planetary magnetic fields. The solar wind normally dominates ion tail structure, but near Jupiter, the planet's magnetosphere takes over. Plasma interactions create visible changes in coma structure. Ionized molecules get pulled along magnetic field lines instead of flowing radially outward. The whole thing becomes asymmetric, chaotic. If 3I Atlas has any internal systems, any technology, any mechanism that involves electromagnetic processes, Jupiter's magnetosphere will stress it. Current loops will experience induced voltages. Magnetic sensors will saturate. Any active electronics will face radiation doses that would require significant shielding to survive, and we'll be watching. Multiple telescopes are already scheduled to observe the encounter. Hubble, the James Webb Space Telescope, ground-based observatories in both hemispheres, radio telescopes, infrared arrays. Scientists are coordinating observation windows, planning spectroscopic analysis, setting up real-time monitoring protocols. They're scheduling shifts, arranging data pipelines, preparing analysis software. This isn't just academic curiosity. This is recognition that the March encounter represents a unique opportunity to test hypotheses that can't be tested any other way. You can't put a comet in a laboratory and subject it to Jupiter's gravity. You can't simulate tidal forces at this scale. You have to wait for nature to run the experiment, and then you watch very carefully. Possible outcomes map along a spectrum. At one end, chaotic decay. The object fragments, jets disperse, activity becomes random and diffuse. The anti-tail breaks up. The mirror symmetry vanishes. The whole thing starts behaving like a normal comet that's been through gravitational trauma. That would support natural explanations, suggest that everything we've been seeing is just exotic chemistry and unusual geometry. Weird, but ultimately explicable within conventional physics. Scientists would breathe a sigh of relief. Papers would be written explaining how interstellar objects can exhibit unusual behavior while still being fundamentally natural. The technological hypothesis would fade back into the realm of speculation. At the other end, structural survival with behavioral adaptation. Jets realign to the new gravitational configuration, maintaining their sunward orientation despite the changed dynamics. The object maintains coherence, no fragmentation, no debris trail, no signs of stress. Activity patterns shift in ways that suggest response rather than reaction. The anti-tail persists. The jets remain sharp. Maybe the object even adjusts its trajectory slightly, a small course correction that keeps it on a specific path. That would be deeply troubling. That would force a conversation nobody wants to have. Because structural survival with behavioral adaptation is what you'd expect from something engineered, not something natural. The stakes are existential for planetary science. If 3I Atlas survives Jupiter unchanged, it means either our models are so incomplete that we can't predict basic responses to gravitational stress, which would call into question decades of cometary physics, or this object isn't behaving like a comet because it isn't a comet. There's no middle ground. You can't have it both ways. Either natural processes are far more sophisticated than we've ever observed, capable of producing stable, self-correcting structures that resist tidal disruption, or we're looking at something that was designed to resist exactly this kind of stress. Jupiter will reveal whether the behavior we've been observing is passive response to environmental conditions, or active management of trajectory and configuration. It's a test, not a verdict, but a test, and the results will force conclusions that many scientists would prefer to avoid. The encounter is 3 months away, 3 months of observation, tracking, measurement, 3 months to refine predictions and prepare instruments, 3 months to argue about what the data might mean. And then March arrives, and Jupiter does what Jupiter does. It applies force. It creates stress. It reveals truth. Whatever 3I Atlas is, we're about to find out. And the answer will matter more than most people realize. 3I Atlas isn't arriving in isolation. It's arriving during a broader shift in how the scientific community approaches the search for the extraordinary. Because for decades, we've been looking in the wrong places. The old paradigm for searching for extraterrestrial intelligence was built around signals, radio transmissions, laser pulses, deliberate messages encoded in electromagnetic radiation, beamed across space with the intention of being found. The assumption was that intelligence announces itself, that a sufficiently advanced civilization would want to be noticed, would broadcast its presence, would reach out across the cosmic void to say, "We are here." And so we built radio telescopes, analyzed frequencies, searched for patterns in cosmic noise. We pointed dishes at promising star systems. We listened to narrow band emissions. We looked for mathematical sequences, prime numbers, anything that couldn't be produced by natural processes. For decades, we found nothing. Silence, an empty spectrum. And that silence shaped our thinking in ways we didn't fully appreciate. The new paradigm is quieter. It's based on behavioral anomalies. Non-gravitational motion, objects that move in ways gravity alone can't explain. Instead of listening for messages, we're watching for actions. Instead of waiting for someone to call us, we're looking for things that behave oddly, that don't fit the patterns we've cataloged, that move through space in ways that suggest intent rather than inertia, and the shift is already producing results. Oumuamua, the first confirmed interstellar object, showed acceleration that couldn't be explained by outgassing alone. It sped up as it left the solar system, just slightly, just enough to be measurable. Scientists proposed explanations ranging from exotic ices that sublimate in ways we've never observed, to hydrogen icebergs that release gas asymmetrically, to, yes, light sails catching solar radiation pressure. The controversy wasn't about whether the acceleration was real. Everyone agreed it was real. The controversy was about what caused it. Some researchers suggested it was natural, just unusual. Others pointed out that the acceleration profile looked exactly like what you'd expect from a thin, reflective surface being pushed by sunlight, a light sail, technology. And suddenly, the conversation shifted from interesting anomaly to, are we looking at a probe? The debate got heated. Papers were published. Rebuttals were written. But something important happened. The technological hypothesis wasn't dismissed out of hand. It was evaluated, analyzed, subjected to the same scrutiny as natural explanations. That's new. That's a paradigm shift. Artificial intelligence is changing the search process in ways that weren't possible even 5 years ago. Machine learning algorithms can now scan millions of astronomical observations, flagging anomalies that human analysts would miss, patterns in light curves that deviate from expected stellar behavior, deviations from expected trajectories that can't be explained by known forces, objects that don't fit existing categories, that sit in the gaps between stars and planets, and asteroids and comets. The algorithms don't have preconceptions. They don't know what's supposed to be possible. They just flag anything that doesn't match the training data, and then humans investigate. The Vera Rubin Observatory, when it becomes fully operational, will image the entire visible sky every few nights, generating more data in a single year than all previous astronomical surveys combined. Every galaxy, every star, every asteroid, every transient event, all cataloged, measured, tracked. And AI systems will process that data in real time, looking for things that don't belong, looking for motion that doesn't fit gravitational models, looking for brightening patterns that suggest active processes rather than passive reflection, looking for the anomalies that might indicate something we've never seen before. The scale of the search is increasing exponentially, and with it, the probability of finding something genuinely strange. Non-gravitational modeling has improved dramatically. We can now distinguish between passive forces, like radiation pressure and sublimation, and active forces that suggest thrust or control. The math is sophisticated enough to rule out false positives, to separate comets with unusual outgassing patterns from objects whose motion suggests something else entirely. When Oumuamua accelerated, scientists could calculate exactly how much force was needed, what kind of surface area would be required if it was radiation pressure, what the mass estimates implied. The numbers worked for a light sail. They didn't work as well for outgassing. That doesn't prove anything, but it narrows the possibilities, and interstellar objects are now priority targets. Because they're not gravitationally bound to our sun. They're passing through, visitors from other stellar systems, carrying compositions and structures that might be completely alien to what we know. If there's technology out there, if there are probes or vessels or autonomous systems exploring the galaxy, they would look like interstellar objects. Fast-moving, unbound, possibly exhibiting non-gravitational acceleration as they adjust course or orient solar collectors or manage their trajectories through planetary systems. They wouldn't be broadcasting. They wouldn't be announcing themselves. They'd be doing their jobs, whatever those jobs are, and we'd only notice them if we were paying very close attention to the right things. Oumuamua retrospectively becomes important. At the time, We had limited data. One telescope, a few weeks of observation, basic spectroscopy that told us almost nothing about composition. We measured its motion, tracked its light curve, noted the unusual elongated shape implied by its brightness variations. We missed things. We didn't have the protocols in place to fully characterize an interstellar visitor. We didn't mobilize every available telescope. We didn't coordinate spectroscopic campaigns. We didn't treat it like the unprecedented opportunity it was. By the time scientists realized how significant it was, by the time the debates started and people began proposing technological hypotheses, Oumuamua was already too faint to observe. It had left the solar system, fading into the darkness, and we lost our chance. We lost our first chance to study an interstellar object in detail because we didn't recognize what we were seeing fast enough. That won't happen again. The protocols exist now. Alert systems are in place. Observation networks are coordinated. When the next interstellar object arrives, and it will, we'll be ready. Telescopes will swing into position within hours. Spectroscopy will begin immediately. Trajectory analysis will run in real time. We'll characterize it fully, measure everything we can, and we won't let it slip away into the dark without understanding what it is. Science advances by admitting blind spots. For a long time, the assumption was that extraordinary claims require extraordinary evidence, which sounds reasonable until you realize what it meant in practice. Anything that suggested technology or intelligence was held to an impossibly high standard. You needed absolute proof, unambiguous signatures, smoking guns, but that standard was asymmetric. Natural explanations, no matter how strained or complex, were accepted with far less scrutiny. You could stack 5 or 6 unlikely mechanisms together, tune parameters to improbable values, invoke conditions we've never observed, and that was fine as long as it was natural. The bar was lower, and that asymmetry meant we weren't actually evaluating hypotheses fairly. The new approach is to evaluate all hypotheses on equal footing. Let the data decide. If natural models fit, great. Accept them with appropriate confidence. If they don't, if they require too many assumptions or contradict observations, consider alternatives. Not with enthusiasm or bias, but with the same rigor applied to any scientific question. Technological hypotheses shouldn't be accepted easily, but they shouldn't be rejected reflexively either. They should be tested, modeled, evaluated against the data, just like everything else. And if they fit better, if they explain more with fewer assumptions, then they deserve serious consideration. 3i Atlas is not proof of anything. It's proof of ignorance. Proof that our models have gaps. Proof that the universe can produce phenomena we don't fully understand. Whether those phenomena are natural or technological is less important than the fact that we're finally asking the question honestly, without apologizing for it, without treating it as fringe speculation. For decades, the idea that we might encounter evidence of intelligence in our own solar system was dismissed as science fiction. Now it's a legitimate research question with funding, peer-reviewed papers, and institutional support. Researchers can study interstellar objects and propose technological hypotheses without destroying their careers. That's progress. Intelligence may not announce itself. It may not send messages or build obvious structures. It may move quietly through space, observing, collecting data, avoiding detection. Why would an advanced probe broadcast its presence? What would be the purpose? If the goal is observation, if the mission is to study stellar systems and catalog worlds, you'd want to be quiet, unobtrusive, easily mistaken for natural objects. A comet is perfect camouflage. It explains the outgassing, the trajectory changes, the presence in the inner solar system. Unless someone looks very carefully, unless someone notices the geometry doesn't quite work or the energy budget doesn't close, you'd never suspect anything unusual. Or it may not exist at all. the universe may be empty of other minds, and every anomaly we observe may have natural explanations we haven't discovered yet. Maybe we're alone. Maybe intelligence is so rare, so improbable, that we're the only example in the observable universe. Both possibilities are humbling. Both require us to expand our thinking. If we're not alone, we need to reconsider what intelligence looks like, how it might manifest, what signatures it might leave. If we are alone, we need to understand why. What makes Earth so special? What barriers prevent the emergence of technological civilizations? The reason 3i Atlas matters, even if it turns out to be entirely natural, is that it forced astrophysics to confront its assumptions. It showed up in our solar system, behaved in ways that don't fit existing models, and refused to be easily categorized. And instead of dismissing it, instead of filing it away as an outlier or an anomaly to be explained later, the scientific community is taking it seriously. They're building new models, testing new ideas, admitting uncertainty, publishing papers that explore multiple hypotheses without committing to any single explanation. That's progress. That's how science should work. Not defensively, not protecting established ideas, but openly investigating whatever the universe shows us. In March of 2026, Jupiter will subject 3i Atlas to forces that will reveal its true nature. Whether it fragments or survives, whether it adjusts or collapses, the data will reshape our understanding of what's possible. And regardless of the outcome, the fact that we're watching, that we're prepared to consider multiple explanations, that we're willing to admit we might not recognize the extraordinary when it arrives quietly, represents a fundamental shift in how we explore the cosmos. 3i Atlas didn't announce itself. It didn't broadcast signals or display obvious technology. It just showed up, looking like a comet, behaving almost like a comet, except for all the ways it doesn't. And that might be the most important lesson of all. Intelligence, if it visits, might not look like we expect. It might look like noise, like anomalies, like things that make us uncomfortable because they don't fit our models. And if we're not careful, if we're not willing to question our assumptions, we might miss it entirely.